The concept is ensembling techniques. So the difference between bagging and boosting. Ensembling techniques, that is what we are going to discuss now in this session. Today, the participant count is too low, but it's fine. Yeah. Okay. Hmm. So before going to describing the ensembling method, so let me again show you. Yesterday, anyway, I showed you what exactly ensembling methods are. This for the to explain this concept. Two good resources I found. One is Medium article. One is analytics with this is Datacamp. Okay, these two are really nice explanations I found. And let me show you an proper definition of ensembling methods. Okay, and we'll explain from there. So IBM resources, as I mentioned yesterday, it is really good. If you are interested, yeah, you please can go and enroll this one, machine learning with Python. Okay, it is free of cost. There you can even do the algorithms and labs also there. Okay, so that you can practice, and at the end you can even gain the certificate once you write the examination. Okay, 20 questions will be given to you, and then examination is there for yes. One badge also will be given. That badge anyway from IBM. That is one thing, and one more thing is it will give you a confidence. Like yes, you learn something and you can easily clear this. Or if you wanted to do it later, for example, after clustering, that is also okay. You can. Right. So anyway, we discussed about KNN, right? Decision trees we discussed, logistic regression we discussed, so SVM also we discussed. You can directly go through the materials and then understand. And if there is anything new which was not covered in our classes, that is again added knowledge. Okay, you can go ahead, and this is all about machine learning with Python course. It is from cognitiveclasses.ai. You can find that in cognitiveclasses.ai from IBM. Okay, it was an IBM initiative. Okay, so what is ensembling learning then? Let us try to understand what is exactly ensembling learning. So actually, for example, uh, okay, let us take this as here. For example, uh, one apple is there. Okay, apple. So the goal is data set is there. We are giving it to machine learning model, and we wanted our machine learning to predict. We will give a data pick image, you can say, to machine learning model. We are expecting our model to predict whether that image is apple or not. This is what the use case. Okay. So in order to do this, from this use case, we wanted to predict whether the data point is apple or not. That means we are going to classifying the things, classify the things. In order to do the classification, earlier we discussed there are multiple algorithms are there to do this. One is logistic regression. The second one is SVM. If you want, you can add what all algorithms are there. If you're interested, you can unmute yourself and then add SVM, logistic regression. Anything popping out from your end? Okay. So decision trees, k nearest neighbors, and naive base. Okay. These are the algorithms that we already discussed. We can use any one of these algorithms to predict whether their data point is or data picture image is apple or not. Let me take logistic regression. It is, let us say, predicting with an accuracy of 86 percentage. And SVM is giving 89. Decision tree 88. KNN 90. Naive Bayes 82. So these are the different accuracies that I got from different machine learning algorithms. Okay. Then ultimately, what you will do, out of all this, KNN is giving us the better accuracy. Then we will go with KNN for this particular problem statement and data set. Okay. So this is in general we do, but we are using multiple algorithms, and every algorithm do follow its own hyperparametrical way and also do follow its own way of learning and then come up with their results, isn't it? So if there is any one standalone system or standalone method which can help which can help us to combine these processes and to combine these all algorithms together and can provide us one standalone model prediction, okay, then that is what we really need to learn. And that's the concept of ensembling learning. Here, if we read this statement is very clear. Ensembling techniques or learning is what it do is it combines multiple learners. Why? Why to combine? Because in order to improve the predictive performance, that is what ensembling techniques do. Okay, ensembling techniques, that is what it do. We already discussed this yesterday. Bias variance trade-off. Bias means error comes with training, and that variance error measured in testing. So both high bias and high variance both are not good. So high bias leads to underfitting, high variance leads to overfitting. But we need a model which is trade-off, bias variance trade-off. Then how do we achieve that bias variance trade-off if we encounter? We already learned about regularization. That is one concept. Another way we can even follow, okay, so we can even follow ensembling techniques. Yesterday I showed you this thing, ensembling techniques, how it works, and I mean just a brief introduction only I have given to you. There are three techniques: bagging, boosting, and stacking are there. But anyway, stacking is not discussed here. Not we are not going to cover. Only bagging and boosting. There only we focus more. Okay, so bagging algorithms are one such algorithm is random forest, and boosting, adaptive boosting, gradient boosting, and extreme gradient boosting. That is what XG boost. Okay, these are the algorithms which are going to cover. Okay, so I am going to discuss random forest today, and we can see remaining. I mean, if time permits, we will also cover XG boost or gradient boosting or ADA boosting. These are all boosting algorithms. Once I explain you the difference between bagging and boosting, then it is really easy to you itself to explore that from your end. Okay, it is simply an algorithm which is bagging and boosting, but you have to understand what exactly bagging do, what exactly boosting do. That's it. If you understand that thing, that's the secondary thing is are very easy. Okay. Now let us understand what does these two do. Bagging and boosting do. Okay. Focus first bagging. Imagine you have a bag, where you can keep the things. So the same concept, bagging. Okay. Bagging actually follows bootstrap randomizing. Bootstrap, STRAP. Bootstrap randomization. Randomization. What exactly this bootstrap? Bootstrap, according to the statistics, bootstrap means bootstrap randomization means we can select some random values out of it. For example, if I ask you to select three random balls, okay, let us say we have 10 balls, random balls of different colors, red, green, blue, anything. If I ask you to do a random guess or random selection of three balls out of the you know this bag or out of the basket or bucket, okay, you can pick any three randomly chosen balls. If that balls are, what my estimation is, I want out of three, okay, out of three, two at least red. I want. I want at least two red. If all three are red, it's okay. But at least two reds I want. Then if you randomly picked and then checked yourself, there are not two, all out of three, there is no red, all are green, let us say. Then you replace it again with the current ball and then again pick, right? That is what replacement, randomization, and then with replacement. That is what bootstrap. Okay. If you go and check it in Google, that is same thing will come. So what X is bootstrap? Strap randomization, random, random in statistics or probability. It is resampling and existing samples. Okay. So multiple new simulated samples. So it is actually replacing. Okay. Repeatedly taking out with replacement. See, repeatedly taking out from the known samples with replacement. This is what really important. Bootstrapping, that is what. Okay. So these algorithms works with bootstrap. Which one? Bagging. Okay. Bagging. Got it? So now what we are going to do, this is the actual data what we have. This is the actual data what we have. So what we will do is we will randomly, I mean, bootstrap randomization. We are doing bootstrapping. Means randomly we pick. See, we know that out of this actual data, 60% or 80% goes to training. Got it? Goes to training. And 20% left for testing. We know that. So out of these 80%, what it will do is randomly some points were taken out or randomly some data is taken out. Okay. That we we will use one algorithm. Okay, we will use one algorithm and we will train. Okay, we will use one algorithm and we will train and we will expect one value. This is what model one, you can see model one. Okay, so we will use what bootstrapping means. The data points again can be back to the original and can again randomly take some more set of values. Again, we will use one more model. Okay, here you can see bootstrap samples. If you clearly observe my screen, okay, it is bootstrap model. Let me maximize this thing and also let me move the screen to down. Here you can see bootstrap, right? It is very clearly mentioned. Bootstrap samples, right? So that means some data set. This is also bootstrap. Okay, this is one bootstrap samples one, and we will take one more bootstrap sample. We will take one more bootstrap sample. Sorry, we will take one more bootstrap sample. Three different bootstrap samples been given to three different models, and we will get three different set of outputs, and we will aggregate. And aggregation concept works in predictions, like in mean regressions. Aggregation of means will happen, aggregation of those results. But here we will go for majority voting. Majority voting, what exactly we got majority voting, that we will take into consideration. And this is called parallel. This is works as parallel combinations. This is how bagging concept work. Is it clear? Bagging ensembling technique works like this. Okay, so different models we can use. I mean, same algorithm. We can use same algorithm, and but with different data points. Here, bootstrap sample once means any some random points out of the training data set, and then we will consider this and we will test with that. If and we will say, "Look, okay, smile is the one we want. Okay, to predict. Yes, we got smile. Okay, super. One is correct. Then again, the samples again get back to their original position and again randomize again. Some random points again can take it. This randomization can be repeated because bootstrap means what? Replacement, right? Sampling with replacement. That is what bootstrap means, right? That is what we do again, and we go for again model two, and then uh, okay, bootstrap and again on the same model we will test and we will see whether we got the expected output or not. No, we did not get. So far we can increase n number of times, and you can even add one more, but this is parallel. You can see parallel. So majority voting we will consider here classification problems. In regression, simple we will do the summing of or aggregation. Aggregation we use. Aggregation can be mean anything, right? Mean in general mean. Okay. This is what bagging. This is what bagging. This is all bagging. Come to the boosting then. The name is very simple to understand. Where is my cursor? Yeah, here. This is what boosting. Okay. So boosting algorithm is again actual data. Here's there is no bootstrap. Yeah, here also bootstrap. Sorry. Here it is again bootstrap samples. But what we will do is instead of parallel, here we consider it as sequential. Sequential. Instead of parallel, the difference between these two is this is parallel. This is sequential. You can see this is being fed to the next model. Okay. Here what we are feeding is what we are feeding here. You can see the model output along with the model output. Okay. So model output, it will have one idea. Okay. How many rights and how many wrongs are there? Here there is no idea. Right. It is not depending on the previous models, but here it is being feeding to the next, feeding to the next, and feeding to the next. How many models we consider that many, and we will take the last one's consideration. Okay. So here there is no majority voting something like that because we are sequentially we are considering. This is what boosting algorithm gives us. Okay, simple. And it is also same for regression also. Regression means also that we are going to predict the continuous value, and in classification we are going to predict the class, right? Class means this is the way to predict the class. The final class is what really important. Okay, understand? Is this basic difference clear? Can I get a quick confirmation? Is this basic difference between those two clear? Hmm? Maria, Prajwal, Jnanish. Is there basic difference between bagging and boosting clear? Okay. Yes, from Prajwal.
Yeah.
Mm-hmm. Okay, Janish. Fine. Okay, same thing. Here you can see bootstrapped samples means randomized samples can be taken out, and then learner one. Yes, yes, yes. So we will take the majority. Majority here, yes. That is why the answer is yes. Got it? This is what bagging do. But boosting. Okay, what happens in boosting? Boosting is here. What we will do is here you can see boost has many variations, but they always follow the same general procedure. It is very clearly mentioned that, here it is what important. That resultant learner is typically weak, misclassifying many samples in the data, much like bagging, but boosting then samples instances from the initial data set to create again new data set. So it is not like bagging, but it is like prioritize the misclassified data sets first, prioritize this, and again a new learner is going to come, and that is going to learn on the updated data set D2, and then again third data set. Got it? Here you can see first training data model one we got incorrect predictions, correct predictions. Wherever we get the incorrect predictions, those samples again we will take, and again we will ask to learn again. Then we will get some other incorrect predictions. Again, those incorrect predictions again we will include with the data set, then again we will forward. Okay. So this is how, if you do it for multiple times, so like doing, finally it will understand that why I'm continuously getting incorrect predictions. Maybe this is some model or something is missing, some pattern is missing. Then it will understand. It will boost it. That is what we are saying. It is boosting. Okay. And the algorithms majorly used for boosting are adaptive boosting. That is what called as adaptive boosting. Okay. And one more thing is called gradient boosting. This uses residual errors. Okay, residual errors means the difference between error you already knew. Residuals. So it will use that. Here weights are being used. Okay, ADA boost. Here gradient boost means it uses errors. This is the basic difference. But what is happening in stacking? Stacking is heterogeneous parallel combination. Means you can see here base learner 1, base learner 2, base learner 3, upswan base learner n. That means here you can take different algorithms. But here in bagging, it is very clearly mentioned it is using homogeneous parallel methods. Okay, got it? It is homogeneous means same algorithm is here, but what we are doing instead, so we just randomly choose some values and then we'll ask the model to do prediction or classification, or regression or classification, whatever it will do. We will note down that. Okay, again the bootstrapped means again the samples can be back for the next iteration. Samples can be back, and then again some randomization can be taken out. Okay, some random points. Again, we will ask model to predict or classify. So if we again it classifies, oh, yes, okay, fine. Then again we will do. Let us say three times I repeat the same machine learning algorithm only, but with different data points. Randomizes, but number of times we iterate. So how many correct predictions we got? Majority, whatever the majority, that is what the result here. If it is classification or if it is in regression, simple, we will to go for aggregative method. That is mostly mean. That is what bagging. But in stacking, heterogeneous parallel methods means we can take KNN, LSTM, sorry, KNN, SVM and logistic regression or decision tree. Four different types of algorithms we will take at once in stacking, and then we will choose whatever gives the majority of the results that will consider as an output. Okay. And boosting means here also homogeneous only, but the thing is here we will seek parallel sequential instead of parallel, we will use sequentially training. So we will consider the first output and how many incorrect and how many correct. That results again we will pass it to the next time. Okay, and again pass it to the n times how many models we are going to use. Okay, that is what about the difference between bagging and boosting. So now let us try to understand completely about random forest. Okay, the random forest is a bagging technique again. Okay, this is really nice tutorial from data camp bagging. Okay, how exactly it works? See, you can observe five different decision trees. Generally, in random forest, they go for decision trees because different trees at one place we call sometimes it as forest. Right. The same concept applies here. That is where the name came as random forest. Random is bootstrap is there, right? Bootstrapping is there. So random numbers can be taken and then randomly we can give those in random data point to the one decision tree, and then again random points again goes to the second decision tree, third decision tree, something like that. Here, out of five, we used, let us consider five trees in one random forest algorithm. Out of five trees, so we got how many cats? Four is predicting cat and one only predicting as dog. So out of this algorithm, we can say that yes, cat is the one result because majority, right? As I mentioned, that is what we take, right? The same thing here. The programmatically also is very easy. So simple, you have to, use the algorithm properly. That is the only difference. See, random forest classifier is the one you have to pick. This is anyway existing in scikit-learn, scikit-learn ensemble. Scikit-learn ensemble. You can import the random forest classifier and you can pass those X-train, Y-train inside, fit of random forest classifier. Then you will get the results. Okay, accuracy will be given to you. That is okay, but you have to understand that three things: n estimators and max depth. So these are the hyperparameters actually. If you choose different n estimators and different max depth, okay, the results will get vary. That is the only thing you need to focus on. Random forest classifier. Okay, so what are these actually? N estimators means number of decision trees that you want. You can take one, two, three, four, five. Your that is, this is a hyperparameter means you can do with trial and error. Okay, you can consider three or you can test it with some other numbers. It is up to you. And then max depth is maximum depth of each decision tree. You know decision trees, right? Already we discussed about decision tree. In decision tree, the depth is there, right? Depth of the tree, like how many nodes it get in, extended to. That is what depth. So you can mention how much depth that you want, like single depth or multiple depths and all. Okay. Once you do properly EDA, you will get to know that. Okay, if you start doing EDA properly, then you will get to know that how much depth is required, how many estimators we can go for, like three, four, five. Okay, here in the example, it is just given that some random integer between 50 and 500, some random integers. But don't do like this. You can, excuse me, yeah, you can mention the correct numbers, and then you can iterate them. Okay, iterate here 5 times iteration we are going to do. So then you will get the perfect results. That's it. This is all about uh, you know random forest. Okay. So is this clear? Random forest. Is this clear? Random forest. Basically, it is a bagging technique. Bagging technique means same algorithm can be used for multiple times. First thing, and how to use this means bootstrap with repetition. I mean, bootstrap means replacement, randomization with replacement. We will randomly select some data points and we'll give it to decision tree. Let us say we will get the output. And again, some more random values we will give to another decision tree. We will get an output. Likewise, we do for some trees. I mentioned, n estimators. Some estimators, 5 or 6 decision trees we can consider, and majority what it actually gives that will actually consider as an output. If it is regression, aggregation functions can be mean, median, anything can be considered as, and then you can aggregate the results in regression, and then you can consider that will be the final value. Got it? Is that clear?
Yes, Ashwin. Yeah.
Yeah, thank you for confirming. Just a second. I will start boosting also.